at any moment in time.
I mean, it does make sense of things which we take for granted so much.
Yeah.
I mean, things that, you know, if I drop this apple...
Its distance is changing and its speed is changing, and calculus can deal with all of that.
Which is quite in contrast to the Greeks. I mean, Greece
Yes.
is a very static
static,
geometry.
yes, yes, it is.
And here we see...
Yeah.
So, I mean, the calculus is used by every engineer, physicist,
Absolutely,
because
yes.
it can describe the moving
yes,
world.
Yes,
I mean,
and it's the only way, really, you can deal with the mathematics of motion or with change.
there's
Yes.
a lot of mathematics in this apple.
Newton's calculus enables us to really understand the changing world, the orbits of planets, the motions of fluids. Through the power of the calculus, we have a way of describing with mathematical precision the complex, ever-changing natural world. But it would take 200 years to realise its full potential. Newton himself decided not to publish, but just to circulate his thoughts among friends. His reputation, though, gradually spread. He became a professor, an MP, and then warden of the Royal Mint here in the City of London.
On his regular trips to the Royal Society from the Royal Mint, he preferred to think about theology and alchemy rather than mathematics. Developing the calculus just got crowded out by all his other interests, until he heard about a rival.
A rival who was also a member of the Royal Society and who came up with exactly the same idea as him, Gottfried Leibniz. Every word Leibniz wrote has been preserved and catalogued in his hometown of Hanover in northern Germany. His actual manuscripts are kept under lock and key, particularly the manuscript which shows how Leibniz also discovered the miracle of calculus shortly after Newton.
What age was he when he wrote...
he was 29 years old, and that's the time, within 2 months, he developed differential calculus and integral calculus.
Really, in 2 months? So it's all fast and furious when it comes. It's,
yeah.
There's a little scrap of paper over here. What's that one?
Yeah,
Is that a letter? Or?
That's a small manuscript, and Leibniz notes, sometimes it happens that in the morning, lying in the bed, I have so many ideas that it takes the whole morning, and sometimes even longer, to note all these ideas and bring them to paper.
Right. No, I suppose that's beautiful.
I suppose that he liked to lie in the bed in the morning.
A true mathematician, yeah. Spends his time thinking in bed. And I see you've got some paintings down here. So this is
a painting.
This is what he looked like. Right.
Yeah.
Even though he didn't become quite the 17th century celebrity that Newton did, it wasn't such a bad life. Leibniz worked for the royal family of Hanover and travelled around Europe representing their interests. This gave him plenty of time to indulge in his favourite intellectual pastimes, which were wide even for the time. He devised a plan for reunifying the Protestant and Roman Catholic churches, a proposal for France to conquer Egypt, and contributions to philosophy and logic which are still highly rated today.
He wrote all these letters. I mean, that's absolutely extraordinary.
Yeah.
He must have cloned himself. I can't believe there was just one Leibniz, you know.
But Leibniz was not just a man of words. He was also one of the first people to invent practical calculating machines that worked on the binary system, true forerunners of the computer. 300 years later, the engineering department at Leibniz University here in Hanover have put them together following Leibniz's blueprint.
I love all the ball bearings. So these are going to be our zeros and ones. So a ball bearing is a
only
one.
zeros and one.
Yeah.
Now we represent the number 127. In binary, it means that we have the first 7 digits in 1.
Yeah.
And now I give in number 1.
Okay.
Now we add 127 plus 1 is 128, which is 2 power 8.
Oh, okay. So there's going to be lots of action.
Would you show this here?
So this is the money shot. So we're going to add 1. Oh, here we go. They're all carrying. So
this 128, this is 2 power 8.
Excellent. So 127 in binary is 1, 1, 1, 1, 1, 1, 1, which is all the ball bearings here. To add 1, we need, it all gets carried. So this goes to 0, 0, 0, 0, and we have a power of 2 here. So this mechanism gets rid of all the ball bearings that you don't need.
It's like pinball, mathematical pinball.
Exactly.
I love this machine.
After a hard day's work, Leibniz often came here, the famous gardens of Herrenhausen, now in the middle of Hanover, but then on the outskirts of the city.
Something about mathematics and walking. I don't know, you've been working at your desk all day, all morning, on some problem, and your head's all fuzzy, and you just need to come and have a walk. You let your subconscious mind kind of take over, and sometimes you get your breakthrough just looking at the trees or whatever. I certainly had some of my best ideas whilst walking in my local park, so I'm hoping to get a little bit of inspiration here on Leibniz's local stomping ground.
I didn't get the chance to purge my mind of mathematical challenges, because in the years since Leibniz lived here, someone has built a maze.
Well, there is a mathematical formula for getting out of a maze, which is if you put your left hand on the side of the maze and just keep it there, keep on winding round, you eventually get out. That's the theory, at least. Let's see whether it works.
Leibniz had no such distractions. Within 5 years, he'd worked out the details of the calculus, seemingly independent from Newton, although he knew about Newton's work. But unlike Newton, Leibniz was quite happy to make his work known. And so mathematicians across Europe heard about the calculus first from him and not from Newton. And that's when all the trouble started.
Throughout mathematical history, there have been lots of priority disputes and arguments. May seem a little bit petty and schoolboyish, but we really want our name to be on that theorem. This is our one chance for a little bit of immortality, because that theorem's going to last forever. And that's why we dedicate so much time to trying to crack these things. And somehow we can't believe that somebody else has got it at the same time as us. These are our theorems, our babies, our children, and we don't want to share the credit.
Back in London, Newton certainly didn't want to share credit with Leibniz, who he thought of as a Hanoverian upstart. After years of acrimony and accusation, the Royal Society in London was asked to adjudicate between the rival claims. The Royal Society gave Newton credit for the first discovery of the calculus, and Leibniz credit for the first publication. But in their final judgment, they accused Leibniz of plagiarism. However, that might have had something to do with the fact that the report was written by their president, one Sir Isaac Newton. Leibniz was incredibly hurt. He admired Newton and never really recovered. He died in 1716. Newton lived on another 11 years and was buried in the grandeur of Westminster Abbey. Leibniz's memorial, by contrast, is here in this small church in Hanover. The irony is that it's Leibniz's mathematics which eventually triumphs, not Newton's.
I'm a big Leibniz fan. Quite often revolutions in mathematics are about producing the right language to capture a new vision, and that's what Leibniz was so good at.
Leibniz's notation, his way of writing the calculus, captured its true spirit. It's still the one we use in maths today. Newton's notation was for many mathematicians clumsy and difficult to use. And so while British mathematics loses its way a little, the story of maths switches to the very heart of Europe, Basel. In its heyday in the 18th century, the free city of Basel in Switzerland was the commercial hub of the entire Western world. Around this maelstrom of trade, there developed a tradition of learning, particularly learning which connected with commerce. And one family summed all this up.
It's kind of curious. Artists often have children who are artists. Musicians, their children are often musicians. But us mathematicians, our children don't tend to be mathematicians. I'm not sure why it is.
At least that's my view, although others dispute it. What no one disagrees with is there is one great dynasty of mathematicians, the Bernoullis. In the 18th and 19th centuries, they produced half a dozen outstanding mathematicians, any of whom we'd have been proud to have had in Britain. And they all came from Basel.
You might have great minds like Newton and Leibniz who make these fundamental breakthroughs, but you also need the disciples who take that message, clarify it, realise its implications, and then spread it wide.
The family were originally merchants, and this is one of their houses. It's now part of the University of Basel, and it's been completely refurbished, apart from one room, which has been kept very much as the family would have used it. Dr. Fritz Nagel, keeper of the Bernoulli archive, has promised to show it to me. If we can find it.